Verifying or disproving whether we live in a simulation might be far more challenging than it appears. Every step of the verification process could itself be part of the simulation. This creates a paradoxical loop. If you aim to find an error or a bug, your brain might interpret it as a natural rule. This, in turn, returns you to the same uncertainty. Over time, you might stop questioning and simply accept these phenomena as natural laws. However, this acceptance is not the end of the questions. It's merely the beginning. Take, for instance, the mystery of the double-slit experiment. The way particles behave differently depending on whether they are observed or not has baffled scientists for decades. Over time, this phenomenon has been accepted as a rule of nature, despite its enduring mystery. Similarly, understanding whether we are in a simulation requires us to go beyond these uncertainties. Yet with current methods, the answer seems destined to remain elusive. Consider the cornerstone of simulation theory, the render hypothesis. This idea posits that regions of space or time outside our perception are not rendered to save processing power. Even if we could one day prove this hypothesis, there's no guarantee we wouldn't just accept it as another natural law. After all, the movie The Matrix was built entirely around this premise of acceptance. This highlights the need for a method beyond simply finding bugs to test simulation theory. A recent paper brings a fascinating claim to this debate. It introduces a concept referred to as the second law of information dynamics, proposing a new perspective on the universe's fundamental workings and the plausibility of a simulated reality. The law suggests that information entropy must stabilize or decrease over time. This contrasts with the second law of thermodynamics, which dictates that physical entropy increases continuously. This difference proposes a balancing mechanism in the universe's operation. To ground this idea, consider an example. Under the second law of thermodynamics, physical entropy always increases. A hot cup of coffee left on a table exchanges heat with its surroundings, cooling down as its thermal energy disperses. In this process, physical entropy rises because the energy in the coffee becomes more disordered as it spreads. However, in terms of information entropy, the distribution of energy levels among the coffee's molecules becomes more uniform, meaning information entropy decreases. This balance between the two types of entropy provides a fresh perspective on how the universe might operate. According to the paper, this balance between physical and information entropy could only be maintained through a simulation. If we assume the simulation has computational and energy constraints, it becomes evident that the amount of information in the universe cannot increase indefinitely. This limitation presents a compelling argument for the universe as a simulation. However, no experimental evidence currently supports this claim. For example, while some proposals have suggested examining dark matter for clues, no resources have been allocated for such experiments yet. Even if these experiments were successful, there's no guarantee we wouldn't simply accept the results as a natural law, distancing ourselves from simulation theory yet again. The film The Matrix demonstrates this point perfectly. It portrays a world where people accept what they perceive as reality. Alan Turing, the father of modern computing, echoed this idea. If a machine can perfectly imitate our thoughts in our world, does it matter whether we call it real? Similarly, Yuval Noah Harari, a leading futurist, argues that reality itself is tied to the number of people who believe in it. Such perspectives make it seem almost impossible to determine if we are in a simulation. But is that truly the case? The only real way to determine whether we live in a simulation might be to build one ourselves, a simulation that operates identically to the universe. If we can achieve this on a small scale, it would suggest that future generations have likely already achieved it on a much larger scale. In fact, we might even be living in a simulation created by ourselves. However, constructing such a simulation would require immense computational power, energy resources, and the unification of quantum mechanics and general relativity. To gauge how far we are from proving simulation theory, we can examine the current power of our simulations. The most recent models, though groundbreaking, remain far from replicating the observable universe. For instance, the Millennium XL simulation, one of the least detailed models, simulates only 1/132nd of 1% of the observable universe. This may seem like progress considering simulation technology began in the 1970s, but it's clear we are still light years away from simulating the universe. When it comes to resolution, the Flamingo model achieves a resolution 22 million times smaller than the diameter of the Sun. This means that in this model, even the Sun would be invisible. To simulate just our planet Earth at a planetary resolution, we would need to increase our computational power by 3 trillion times. At this point, it becomes clear that the dream of proving simulation theory by building a simulation remains extremely distant. Yet, someday, humanity might achieve it. Until then, the question of whether we are living in a simulation remains one of the greatest mysteries of our existence.